Today we're going to continue with the subject of related rates. Remember, a related rates problem you're given a relationship between two variables. You know how fast one of the variables is changing. And you are supposed to determine how fast the other variable is changing. So when we're talking about the rate of change of something, we're talking about the derivative of that variable with respect to time. So in something like this, there are a number of steps. First, as I said last time, we draw a picture. Secondly, we define variables. Third, you write an equation connecting your variables. Fourth, we take the derivative of both sides. Both sides of our equation with respect to the variable t. And we abbreviate this TD, take the derivative of both sides with respect to t. So we take the derivative of both sides of the equation with respect to time. In a related rates problem, always with respect to time. Then we go ahead and plug in what we know and solve for what we don't know. And lastly, write some sort of concluding statement. So these are all the steps in a related rates problem, and we did a related rates problem last time. I'd like to do another related rates problem with you today. What we're going to do is take a pebble and throw it into a pond. And that pebble makes a circular ripple. So a circular expanding ripple. Everybody's dropped a pebble in a pond and watched the ripple move outwards from the point where you drop the pebble. We are going to say that the radius of that circular ripple expands at a rate of, let's say, 20 centimeters per second. So the radius is expanding at the rate of 20 centimeters per second. And the question we want to ask is this: how fast is the area enclosed, that circular area enclosed by the circular ripple increasing when the radius is, let's say 30 centimeters. Everybody got that? We drop a pebble into a pond and it makes a circular ripple, and the radius of that circle increases at a rate of 20 centimeters per second. How fast is the area enclosed by the circular ripple increasing when the radius is 30 centimeters? Notice that we give radius in terms of centimeters, and we give the rate at which the radius is expanding in 20 centimeters in centimeters per second. So let's go ahead and run through all the steps of the problem. Step 1, as you know, draw a picture. This doesn't need to be complicated. It doesn't need to be fancy, and I apologize for my bad drawing, which is bad enough on a blackboard and terrible on a computer screen, but that potato thing is supposed to be a circle. Step 1, there's our circle. We can imagine that circular ripple expanding. I'm sure in your mind it's perfectly circular. And as you're taking notes and you put this in your notes, I'm sure your picture is going to look better than mine. If at any point you find that I'm going faster than you can take notes, please feel free to press pause on the video and take notes at your own pace. So step 2, let's define some variables. We'll need radius. That's an R for radius. We can do that right on the picture. And we also need another variable. So radius is the variable whose rate we know. We know that how fast that's changing. We would like to know the rate at which area is changing. So let's let A be area. And now that we know our radius, that is a horrible looking R. It's probably a slightly better looking R. Now that we know our radius and our area, we need to do part number 3. We have defined our variables. We've drawn a picture. Now let's write an equation which connects the variables. Well, in a circle, what equation connects radius and area? You should know this well. The area in a circle equals pi times the radius squared. A equals pi r squared. And that's all there is to part number 3. Write an equation which connects the variables. That connects A and R. Now we're going to take the derivative of both sides of this equation with respect to the variable t. So remember, we're not taking the derivative with respect to R, and we're not taking the derivative with respect to A. We're taking the derivative with respect to t, and we're going to use the chain rule to do that on the right-hand side. So the derivative of A is going to be dA dt. The derivative of pi r squared with respect to r would just be, you bring the 2 down, it would multiply the pi. That would just be 2 times pi times r, but we're not taking the derivative with respect to r. We're taking the derivative with respect to t. So after we take the derivative of the pi r squared, we have to take the derivative of r with respect to t, and that by definition is just dr dt. So the derivative of pi r squared with respect to t is 2 pi r dr dt. Well, we're in the home stretch here. We're supposed to plug in what we know and solve for what we don't know. Well, we do know that r is equal to 30 centimeters. Whoops. R is equal to 30 centimeters. And we also know dr dt. So if we look back in the problem, dr dt, how fast is the radius changing? Well, we know that's equal to 20 centimeters per second. So dr dt is 20 centimeters per second. The radius is 30 centimeters. And what we want to know is dA dt. So we want to go back to this equation right here. Now we know all the unknown parts. We know r, dr dt. Just go ahead and plug those all in. So dA dt is equal to 2 times pi times r, which is 30 centimeters, times dr dt, which is 20 centimeters per second. Well, 2 times 30 is 60, times 2 is 120, times 10 is 1,200. So if you multiply the 2 and the 30 and the 20, you get 1,200 times, there's still a pi there. And then if you take centimeters and multiply it by centimeters per second, you end up with centimeters squared per second, which is in fact a unit of the rate of change of area as a function of time, centimeters squared per second. And so we could put in some sort of concluding statement. The area is increasing at a rate of 1,200 pi centimeters square per second. And there you go. A little messy, but that's the solution.